Yes.
But you're sorry, I just betrayed you. Yeah. Also, no one will be a teammate of you. Let's change the color.
Okay, so I'll be by myself.
Yeah.
Wait. Hey, Alicia, are you there? Can you hear us?
I'm here. The sound is good.
Okay. So we cannot hear you.
This is manual, right?
Great.
But it was complicated.
It was
So
complicated.
last time, when there was no issue, I just did it like, I just put my PC here on the camera here, and then just I just did that.
So Alicia, I think we can start, and the recording will be automatic. You will make sure which window will be recorded, right? It's recording anyway, so.
It was young.
Right. I didn't record that. Why couldn't? So that was a problem.
I need to set up something. Are you?
Or is audio working? Like, can people ask questions?
Yeah, it's. So I need to go to the. You go. Okay, you just give your talk.
Some question come out, you have to see how Alicia is not. Sure. Or maybe just take a movie of that and then you just watch that on YouTube. Yeah. Put it on YouTube and.
Okay, we'll have the recording is mirror, that's fine.
Huh? No, it's not fun.
Just give it a talk.
You cannot recognize what the letters are mirrored. I think it's fun.
You can begin. Can you start introducing speaker, then you adjust your Zoom stuff.
Like if you can just rewrite it again.
We are very happy to have our speaker Yama here, and Yama he just received his PhD in Pittsburgh, and he will go to he will go to INFN in Italy to start his postdoc. Yeah. Let's welcome.
Okay, thank you. Thank you for the invitation, and thank you for the introducing myself and the thing. So I'm Yang Ma. I'm from the University of Pittsburgh, and I just graduated. I got my PhD degree, and I will move to Italy. Basically, it's IFN at Bologna, or also in, I think it's kind of a joint with the University of Bologna in Italy for my first postdoc. So today I'm gonna talk about the Partonic picture and the standard model expectation of future ultra high energy electron colliders. So mainly it's about the muon collider, but the things I talk about here is also kind of more or less valid for the clique, and also to some extent it's also true for the C cube or ILC or CEDC, those kind of lower energy electron colliders. So here is my outline. So firstly, I'm gonna talk about the background. Yes, our goal, what we are working on. We start from the mysteries in the standard model, and then I'm going to talk about a little bit about the machines, the colliders, and especially the high energy Lepton colliders that's in the roadmap in the future. And I'm going to talk about the Partonic picture at those colliders, Lepton colliders. So I'm going to introduce a little bit about partons and PDFs. I'm going to talk about we can start from the equivalent photon approximation, EPA, which is also known as Williams-Whittaker approximation. And then we can go beyond it to talk about the evolution, and using the evolution to get the PDFs, and also we're going to have the parton luminosities to show the physics. And using this picture, I'm gonna show a little bit about the standard model expectation for this future high energy colliders. So we're gonna also start from the EPA, and then I'm gonna let you know that I'm gonna show how much the picture will change after we consider all the partons and the evolution and the PDFs. And then I'm gonna have the summary. So firstly, is our goal and the machines, a little bit about the background. So here is, maybe I don't include more here, is those things we don't have in the standard model. So we don't really understand why we have the electric symmetry breaking, why it occurs. We don't know what's the history of the electric phase transition. We don't know why we have the hierarchy in the fermion masses. We don't know the nature of dark matter, where it comes from, what it's made of. We also don't know where the matter-antimatter symmetry comes from. Also, we don't know the mechanism that generates the neutrino mass. Also, here we don't know the dark energy. We don't know the quantification of the gravity. We don't know why there is cosmic inflation after Big Bang. So all of those things, we don't have any explanation in the standard model of particle physics. But for all of those things, we need to look for the physics, new physics beyond the standard model. So this is everyone here working on. So our goal on the colliders, that's we as collider phenomenologists, and what we do. So we wanna address those big questions, and we wanna explore something new to have some new discoveries. So we have two strategies. One is we study all the known phenomena at high energy colliders as somewhere else, better and better, to see if there is any indirect evidence for the new physics. That is, we go to the precision frontier. So that's why we want to increase the luminosity of RC to have the high luminosity upgrade. That's what we do. Another way is, we can try to go to the energy frontier, to go to very, very high energy colliders, or we to go to cosmic rays to look for that. For if there is direct evidence for the new physics, based on physics at energy frontier. For example, if you see something very heavy, 3 TeV or 5 TeV particle there, that is new physics, right? Of course, we don't see that right now. And also we have the colliders. We have the hadron colliders, which collide either the proton like LHC, or proton and proton like Havitron. And that is, we use them to reach the very high energies. And also we have another one is Lepton colliders, which is right now it's only for E plus and E minus to reach the high precisions, because that is fundamental particle. We can imply the full energy of the machine for the collision, and also we can avoid the large QCD background like what we have at HC today. So that's the advantages of the Lepton colliders. So here I steal this page from some talk at SNOMAS conference this year. So this is the machine in the plan. You see this is for the Higgs factories. We have the Hadron RC, of course, RC generated the Higgs is there. Higgs was discovered, so that's a Higgs factory. We also have other things for those are all Lepton colliders. You see the CQ or ILC is around 200 GeV, 250 GeV, a click, and 380 GeV. Those things. We even have a muon collider for the Higgs factories. That's because you're gonna benefit from the larger mass of the muon. So you say the muon mass is around 200 times larger than electron mass. So as a Higgs factory, you can generate around 40,000 more Higgs than E plus version of the Higgs factory. But the physics is more or less the same. And here we also think about, we dream about the multi-TeV very high energy version of the colliders. We have, of course, we have high energy FCs, those are the and SPPC, FCC, HH, those are the hadron colliders. We also have high energy version of the lepton colliders, the colleague, around 3 TeV, the E plus E minus linear collider. Also, we have our dream machine, the muon collider, which is around 3 TeV. That is what we are discussing right now. But we hope in the future it can go to 10 TeV or even beyond, like 30 TeV or something. So I can also talk a little bit more about our dream machine, the possible muon collider. So I'm going to show the advantages. So here in the left-hand side, this is this one is the size of formula. And inside here, you may see a blue circle is which diameter is around 2 kilometers. That's the size for a 3 TeV muon collider. And this one and that one, I think this is 20 or 30 kilometers. This is for ILC. This 50 kilometers is for colleague. And this one, a diameter 8 kilometers something. This is for the current LHC. You're going to see that if you count the land is expend some money. You see the muon collider offers a precision probe machine in a very smaller, a much smaller footprint. Right? Another way, one is also this. I also borrow that from the Snowmass talk. So this is here is for the collider machine energy. This is the luminosity per energy. So we see this one, the red one is for the muon collider. So it's almost the most power efficient machine at high energies that we can imagine. So that's also kind of in the technology way why we think this is kind of great. And also I want to show a little bit about the implementation of this muon collider. So we notice here we have two ways. One is to have a proton, and you have from proton you're going to have the pion, and after pion you decay you have the muon. But in this way you need something called cooling. 6-dimension cooling means you want the muon is 3-dimension is for rotation, 3-dimension for this momentum. You want it to be there. That's the cooling before you accelerate it. Another one that's kind of an old generation, but it's more mature. And another one is called lemma. So you can have a very boosted positron to collide with the rest electron, and then you have electron-positron to muon plus muon minus, and then you generate the muon. So in this way, the cooling is not a problem, but it's a little bit challenging to acquire higher luminosity. But this is both ways are possible that people are working on that. I just want to show that it's possible to build such a machine, a muon collider. And then I want to show why we want to have a high energy lepton colliders. So,
sorry, could you go back?
Sure.
I just had a question. So
Yeah.
this first scheme, acceleration is happening in the linear sections, or it's sort of circular?
this one
Yeah,
is circular. You see the acceleration parts, they are the same.
they're the same.
Yeah, acceleration part is here. This linear part is only for the cooling. So I'm not an expert there, but you see the two versions, they are before
I know
this.
about the second one,
Yeah.
but the first one, you're saying that the acceleration happens in this red circle.
Yeah. Both of them they are the rest. You see, they are the same. Acceleration and the collider ring, they are the same. The only difference is how to produce this muon beam. Okay, sure. So we come back to physics. So why we think high energy lepton collider is great? So firstly, if you think about lepton collisions, we can we can get use of the full machine energy. So if you think about this, this is a plot I take from the muon symmetric guide. So this line, this vertical axis is for the machine energy of hadron collider. This horizontal is for the machine energy of this muon machine. We see that as 10 TeV for 10 TeV machine, a muon lepton collider, it can easily go beyond 100 TeV PP collider. well, that statement is kind of a process dependent, but as we know, 10 TeV is also not our limit. It's just a benchmark point. So that's kind of the advantage of the muon collider, obviously high energy electron collider over this PP collider. On the right hand side, we have something more in physics, because right now we see there are at very high energies, we have two mechanisms. One is a lepton collision, that's mu plus mu minus, or E plus E minus to some final states. For 2 to 2 is this, right? And another one is this vector boson fusion. So we have two different mechanisms. And so for here, if I show that, for example, it's mu plus mu minus to T bar production at low energy range, of course, the mu plus mu minus annihilation are dominant. But if you go beyond high energy range, this 2 to 4, this VBF is dominant because of this logarithmic enhancement. So in this way, people call this a high energy lepton collider, not only a lepton collider, we also call it VBF colliders, vector boson fusion collider. So in order to study this well, we notice there's log S over M, well, this is very big scale. We have we meet very big logarithms. We need to resum these large logs to have more accurate results. So we need to look into the Partonic. So then allow me to talk about this Partonic picture, which is based on.
Can I go back one slide at the VBF picture? Why? What's the n power n there in the VBF process?
This n.
Yeah.
Oh. Because this is just let me think how to say that. Because this is just one example. If you look at more higher orders or more lags, you're gonna, I think you may see something like this. More lags, more higher orders. You have this different orders of you can always generate that as alpha. Assume is usually you see that in QCD, so people write that as alpha s, alpha my, and log and you can write the cross section in the expansion of this way. So the leading log term is you expand all the this part, the first term of that. Is that clear?
Yeah, but why it's a cross section for a given process shouldn't depend on the power of n you choose.
Yeah.
So what's the n here?
No, this is just for one. It's no clear.
Yeah. So I assume at leading order the n equals 2.
Yeah. So then we talk about the Partonic picture. This part is based on my collaboration with my supervisor Tao Han and his postdoc Kapinxie with these two papers. And so firstly, let me review a little bit what we are talking about. So we can go back to the hadron colliders. For the PP collider, obviously the SPP bar S, where the W and Ds were discovered. Or Tevatron, the proton antiproton collider, where top part was discovered. Or LC, where Higgs was discovered. So for LC, we have proton collision. That's what we have in the machine. But at the collision point, what we talk about is actually, you see, QQ bar collision, QQ bar annihilation, gluon fusion, those things. So actually what happens in this hard scattering is something inside this proton. It's called parton. And then we introduced, in this formalism, we introduced the PDFs, which is called parton distribution functions, like F, A, B. This stands for the probability to find a parton small a from a beam particle capital A. And also the one from parton small b from the beam capital B. So in this way, we call that factorization formalism, so that the cross section AB to some final state can be written as the integration over this x1 and 2 as A and B are the momentum fractions of the parton that takes momentum from the mother, and those are the PDFs. And this sigma height is the so-called hard collision process, the cross section. That's what we know. Is we have this. The reason is we know hadrons are composite, so we need to borrow this picture. But however, if you move to lepton colliders, they have one question. Because leptons are elementary particles. There's nothing inside the proton. There's something inside the proton. You have quark and gluon, but there's nothing inside the electron. There's nothing inside the muon. So why do we still have this kind of PDF formalism? The thing is, we go back to learn the Williams-Whittaker approximation of this EPA. So if we assume this this lepton, or it can also be quark, it's moving very fast and it's very energetic, it will be able to radiate out the collinear photon. So if you want to calculate this process, what you can do is you can factorize that thing into, this is the total cross section, into 1 for the photon, the probability to find the photon inside this lepton, and also the other one is photon and some other initial particles get the final space. So we have, this is the hard cross section, this is the so-called photon PDF from the EPA, where it looks like this. This alpha is the coupling, QED coupling. This is the so-called splitting kernel, and this is the log term. We have the log term. That is very well known and very widely applied. So with this thing, we can use at lepton colliders. Like what we can do is to also something. This thing looks like very like what we do at hadron colliders. So we can study the photon-photon collision at lepton collider. We can also study the so-called ISR, initial state radiation. So we have this photon radiated out before the collision happens. So we can radiate out one photon on one side, or one from the other side, or at higher order, one from both sides. We can do the resummation on that. So that thing is, if you have ISR, some energy is taken away by the photon, and then this the collision energy of this here, this lepton is lower. And then, as we know, that the S channel processes, the cross section is have a 1 over S behavior. You have lower collision energy. You have a bigger cross section. So that's the part we need to take into account.
Sorry. So this photons assumed to be soft.
Yeah.
So it's quite soft.
Not necessarily.
No, you have the slot. You also have some collinear. It's not that much though. But for the general picture, yes.
In Weizsäcker-Williams, the photons can take however arbitrary amount of energy, half very easily.
You can yeah. For the photon PDF, yes. But I mean, you can have something like this. I'm going to show you some kind of plot there. But you're gonna, if you talk about electron, right? It's a round peak around here's X, just PDF. It peaks around 1 here. That's right. That's for the ISR, its photon itself takes not that much energy, so that the PDF still peaks around 1.
Mm-hmm.
But for this, yes, the other way also right. This is for photon. It's time to be solved. So the PDF is kind of larger in the small X range and smaller at high X range. That's how it looks like. But it doesn't have to be solved. You can still have a kind of photon here, but the thing is small. Is that clear?
So it's not like soft collinear effect theory. Some.
Oh no, a different language, but kind of same picture. And then we want to go beyond the EPA to see whether EPA is good enough. I mean, it is. We want to know the reason. But if it's not good enough, we want to see in which direction we can expand, we can improve. So here is one thing we do the test. We have electron, muon, 2 electron, W, and neutrino. So we say if we do the fixed order calculation, it's 2 to 3. They have all these famous diagrams here. So here this can be photon or Z, photon or Z, or photon, and this is W. And here, this plot is, we see the solid curves for FO means the fixed order calculation. Of course, there's some uncertainty in high energy range around 10 TeV, 100 TeV. And the dashed curves, those are for EPA. So they overlap in the small energy range. That means EPA works very well. And we want to know why. And also we notice that EPA start to fail at some place, so they don't overlap. We also want to know why. So in this way, we calculate this process and show this distribution of the virtuality cube. So what we say here, this black curve is for the full, if you include all the diagrams. But if you include only the photon and W1, it overlaps with the R1 in here. So that means the forward photon contribution is dominant. That's why the EPA works. However, if you go, we also have other Z or W diagrams, and also in this way we don't plot out the interference between those things. So if we include only part of this, if we only include photon diagrams, if we only include Z diagrams, if we only include W diagrams, we show this this plot from cross section over the machine energy, over the collision energy in this way. So we say this black one is for if we include all the diagrams to ensure the gauge invariance. Oh, that's good. Or if we only include the photon, or if we only include other things, it will start to be unphysically big at some high energy range. So here is my two comments here. One is, firstly, as we know, the gauge invariance requires you take all the diagrams. That means you need to take all the things here, not just the photon. So that means if we go to high energy range, high scales, we need more partons, more PDFs for those partons, not just only for this EPA. So that's the reason why we want to go beyond the EPA. Is that clear?
Sorry, the last diagram, you say the EPA fails. Say it again, why it fails?
This one?
You have 3 plots, the last one.
Yeah, this one.
Yeah.
EPA fails at some high energy range. That's because when the energy is high, is here. EPA is like you in these diagrams.
You're missing the Z contribution.
Yeah.
Interference.
Yeah, the day is mixing, but what's more important is the interference between them is mixed. So all the contributions, if you take them individually, they're kind of positive contribution, but there is negative interference to make sure the gauge invariance. That's why you have a finite.
So what's the goal here? To have a more reliable approximation? Because when it's a weakly interacting theory, I can, in principle, if I'm good enough, I can just calculate it.
So the goal here is we want to know, because we know there are more partons here, but we want to know when the EPA fails. So when we want to introduce the electroweak, like W and Z as a parton. So this more or less someplace in the high energy range. So that's is only one way to see. It is to show it is necessary to talk about the electroweak.
I don't understand.
So let me answer slightly differently about the same question.
Okay, sure.
So why do I want to do this calculation? Why don't I just do perturbative calculation?
You want to do the 2 to 3?
Yeah, I can do that.
You notice here. You can do 2 to 3. You can do 2 to 4. You can do 2 to 6.
But so the place you are going to are expert in doing those fixed order calculations.
But they also admit 2 things. One is it is very hard when you have more final states. You have very high energies. And in the Monte Carlo phase-based intro, you do that, you have better. You have larger uncertainties. You need more points in the Monte Carlo. But in this way, if you have the electric PDF, you can capture the logarithm, the behavior. You're gonna be easier for you to have some some predictions in there.
Also, I couldn't believe at 2 to 3 level our computer cannot do precise calculation. So the uncertainty cannot be caused by limited computation power. That's caused by something else.
That's because of a bad Monte Carlo strategy. Trust me, this one is done using laser. If you use MATLAB, you don't have this.
Yeah,
You're not
with
able to do
MATLAB,
it.
I'll get a very nice curve, right?
No, that's the reason we didn't use MATLAB is MATLAB failed at around here.
You know why?
No.
Oh, because the collinear is hard to deal with, collinear emissions. And Wizard has to deal with this collinear emission, collinear divergence, put in a fake scale cut. They require the virtual photon emitted from the initial parton to have a Q square bigger than 1 GeV.
Oh, yeah,
So they put the artificial cut on the scale to regulate the IR divergence.
Yeah, but
MATLAB didn't have that cut. That's why MATLAB fails.
yeah, good to learn that. But you see, Wizard still have something there. We need to to do the parallelization, increase the points for the metal. It will be better, but it takes more.
Yeah, but Wizard as a phase-space integral generator is much worse than MATLAB. They are just different generations in some sense.
Yeah.
But still, we're talking about the small coupling constants, right?
Yeah.
So maybe there is like technical impracticality when you have very many final states.
Yeah.
To calculate it just exactly, right? But I don't see any problem at 2 to 3.
Yeah.
There's definitely not.
This is just a kind of toy model, just one example to show that.
Yeah. So actually, if I ask MATLAB to do this space integral, there's no trouble. They will do that very well. Up to 5-6 body, they will do it very efficiently.
People could do it before any simulation tools, right? Before any math graphs were even written, right?
No, really. Phase-space integral for finite mass doesn't have a closed form for higher.
Sure,
final
but
states.
it doesn't mean that math graph came and now we can do it, right? Everyone can do it,
everyone
right?
can
But
do it.
before, maybe a bunch of specialists could do it, right?
Yeah.
Like lab physics predates math graph, no?
Yeah.
Sure, but when I talk about 5-6 body final states, most generator will be extremely slow. MATLAB is really fast. The reason MATLAB fails should be coming from the first diagram, when there's a photon emitting from the muon that is collinear, and MATLAB there's a collinear divergence. MATLAB didn't know how to handle that. That's why he had to switch to a different, slower generator called the Wizard, who add the artificial cut.
Can handle this kind of better.
By adding a artificial cut on there, on the collinearity of the photon, saying it has to be bigger than a Q square, cannot be smaller than 1 GeV.
Yeah.
So they had a regulator there. But is that regulator fully justified? Is it stable? The process independent is all in question.
Yeah, that's correct. So I'm sure that even before MATLAB, you can do that by better, and they would say, like people from from Pittsburgh, like Iris Bretas, who does precision calculation, have argued like, if you adjust the parameterization properly, you will be able to get a better result. But the thing I want to say is, if you have a PDF tool, by doing that, you don't need to do that to make that effort, because not everyone is expert in the precision calculation. Those are people in the new physics things. They wanna calculate the background if it start. May I continue? So here is the picture. What's left hand side is what we already have in the literature. So we can calculate the lepton collisions. We can use this EPA to calculate photon collisions. We can include the ISR, and also I think in 1980s, the Sally Dawson's company and also Keynes' company, they independently developed this kind of effective W approximation, EWA. That is when the scale is very high, you can so high that the D and W they are more or less can be treated as massless particles. They can be treated as a parton radiated out from the lab. So it's the same diagram with the EPA, but you replace the photon with this WRT. That's called EWA. That's you can find in the literature and in the left hand side. Right hand side is what we want to add to this picture. So firstly, if we include the evolution by solving DGLAP, if we continue doing this is DPA, right? If we continue doing the splitting, the photon will split into a pair of fermion and antifermion. So in this way, it can be lepton, can also be quark. So quark enters this picture. And also, if it is quark, it continue doing the splitting, you can radiate out gluon. In the very end, after this evolution, you will see the colored parton will appear behind a lepton. That's the thing people didn't think about. Maybe they were think about that, which is so-called resolved photon processes. That's the thing. And then, if we also consider the way that EW considers, if we go above the electroweak scale, where we take the day mass as a typical scale, we're gonna take into the electroweak, also turn on the electroweak sector. So we have something like EPA. If we're at the leading order, of course, we're gonna also do the evolution, have like higher order corrections. We also have the corrections from this electroweak sector to all the things above. So my question, so right now I need to answer two questions. One is whether it is necessary to consider D and W. So I was trying to show it's kind of necessary to consider D and W here. And so also I wanna answer the question, how much this correction can the electroweak sector to this QCD sector? So that's the two questions I want to ask, and people would ask, I need to answer. So I also want to show the framework, how we do that. So the DGLAP equations looks like this. It's similar to the ones in QCD, but we have more interactions. So we have alpha I as the index for interaction, can be QCD, QED, electroweak, right? And we also have some initial conditions. We assume that at, for example, muon mass, and this muon PDF is just a delta function. It's very static. So if we need to introduce a scale of a QCD, so below the QCD scale, we only have photon splitting. This is only QED evolution. And right now we set the QCD scale around 1 GeV, something around it. And at this scale, we also don't have this gluon. But this is kind of uncertain. It's because in the low energies we also have QCD, but it's non-perturbative. So we decide to start around at this scale to match the so-called quark parton model, which is kind of matched to the non-perturbative part. So if we continue on going to higher scale, we include both QCD and QED. And then if we continue going up to about the electroweak scale, we need to include everything. And also we want to work in the gauge basis, BW basis, which can be related to the gamma and day basis using this Weinberg angle. And after, sorry.
Here, so F gamma Z is for what?
It's for the gamma Z mix in PDF.
How to mix?
How to mix? Okay, sure. Last thing is for fixed order calculation. You have this diagram. It can be gamma, can be Z, right? But you have two diagrams. So if you take gamma matrix square, that is for the gamma diagram square. If for the day matrix square, it's for the day diagram. But you also have this gamma times day. You have this interference. So this one is corresponding to the photon PDF one. This one is corresponding to the day PDF one. And this one is corresponding to the gamma day mixing. It's the interference. I mean, you wanna do the PDF, and the leading order is just an approximation to the fixed order. You wanna measure that. You don't wanna only have the square of each diagram. You also wanna cover the interference between them. So that's the gamma day mixing. Is that clear?
So if I count that PDF piece with another muon, right? So I'm doing a muon vector boson scattering, for instance. What coupling I should attach to the color scattering?
Yeah. Here, this one is you see alpha, right? Alpha is actually E squared, right? This is alpha, J is actually G squared, right? This is E times G. It's interference between them. It's exactly if this photon diagram, you have E there, this Z diagram, you have G there. This interference is E times D, right? And the thing is, this one can be positive or negative, just like the interference. So I don't want to go this. I don't want to waste too much time in the details, but I have some backup just in case you have any questions. Hopefully, I can answer them. And I just want to show our results for the PDFs. So here is the only contain this QED and QCD PDFs. So this plot is for the electron. This one is for muon. It's more or less the same. We see this one, this black curve is E, valence E. It's just the electron. This is just the muon. So it peaks around. Here is a momentum fraction. It peaks around. I'm sorry, I erased it. As I draw, peaks around x equals 1. But you also have a peak there in the small x range. That's from the summation, because you have softer photon. You have photon, and photon will radiate out E plus E minus. E plus is here, right? Sorry, E minus is here, and the anti-E is this blue one. Is also kind of a peak in the small x range. And this gamma is what we usually have in mind. Is the EPA gives you the thing, and we also have uptime quark, downtime quark, and gluon. So those things they look like the C quark, which peaks in the small x range. So this one looks as the valence quark, which peaks at some place. So this is here is just itself, it peaks at epsilon 1. So that's what we have. And also we choose two scales. One is 30 GeV, one is 50 GeV. So the scale uncertainty for, if they say the bigger one is for the gluon one, it's around 10%, I think. But we're going to improve that. But this is what we have right now. For if you only consider QCD and QCD.
Sorry, why the gluon is much larger than up and down? Because I have to first split the photon to quarks, then quark emits gluon. The gluon in some sense is a higher order in this splitting function.
Yes.
So why gluon is much larger?
This only up, and this only down, not all the quarks.
Then it should be even lower, right? The gluon is a higher order emission.
Yeah. You can see that from here. If you look at the momentum fraction, yes, you have more electron, and then electron radiate out the photon. The photon has something. You have lepton, say lepton, and then you have quark. And the gluon is smaller than quark, right?
Yeah, but on that plot, why?
Yeah, on the plot is this is only D quark, not all the other D type. Not the real one should be D plus S. The U should be U plus C plus, right? We didn't have that. And here, if you go beyond this electroweak scale, we turn on the electroweak sector. So we see. We have everything in standard model as a part. So firstly, we even have neutrino, because that's electron radiate out W, the other side is neutrino, right? And we also have this the C leptons. We also have the quarks. So now the quarks is the quark plus the anti-quark is here, right? So I think that plot answers James' question. You see, if you add them together, the quark is larger than gluon, but gluon is softer. So in the small x range, gluon is larger, and the large x range, gluon is smaller. Right? So here I wanna answer the question why and how big the correction can be from the electroweak sector. So this I just add one comment here. So because of the relatively larger SU2 gauge coupling for the down-type quark. If you look at the electron to down-type quark PDF, it receives around a 50% correction from the electric sector. And also the one from the muon to down-type quark, we receive 100%, which is kind of big corrections from the electric sector. And also we see this, we also take two scales, one is 3 TeV, one is 5 TeV. far from each other, right? And the scale uncertainty is around 15% or 20%, depends on whether you're talking about electron or whether you're talking about muon. So I just try to show this general picture.
Yeah, but just make sure about statement. This statement about 50 or 100% correction is you ask how much down quark I could find in my beam as as parton.
Yeah.
At a very high energy.
Yes.
So
yes.
Of course I have to include the W and
Yes.
then that emission.
Yes,
That's
exactly.
the same size as the photon cell. So in terms of coupling, or it's
Yes,
even slightly
yeah.
larger. That's
Yes.
why this 100% comes.
Yes. 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 And also with those PDFs, we can have the parton luminosities, which is just the convolution of the PDF. So you know how much the combination of the partons there. So again, this is for electron. This is for muon. So we think about the 3 TeV electron E plus E minus machine, or 10 TeV. This is for colleague. This our 10 TeV muon plus muon minus machine. That's for the muon collider. It's possible one. But they are more or less the same. We have E plus E minus 1 in the peak around tau equals to 1 square root tau. So we have this blue one as the largest one is for the photon, and the last one is for the counter scattering. We have this orange one, photon, which is the old one from the EPA. You can also have that. So that, in our understanding, that would be the largest one for the photon collision. But we have something new. We have photon gluon and photon quark. So if we sum them together, it's around 50% to this photon for electron, or 20% to photon for the muon collider. So which is not small. So we need to consider this purple and this blue curves for the luminosities. And also we have something totally new, that is gluon quark, and gluon. So QCD partons combinations, they're very small. They're very small. Around just 2%, or even smaller than 1% there. But if we consider for the QCD jet production, you have a larger QCD coupling constant. You also have the multiplicity for the QCD processes. They may introduce some sensible corrections that we wanna investigate.
That can never be true, right? My dominant QCD jet production are from Joyan process at Lepton colliders.
No.
What's my multi-jet cross section from?
This from gluon jet.
Dijet?
Yeah.
How come?
I will show. So right now we have the Partonic picture. We want to show the standard model expectation of the Lepton colliders. So we want to know what is the standard model picture. We want to know what is the background of the signal if the machine is turned on. We want to know where we can see the possible new physics. But of course, the largest background is the so-called beam-induced background, BIB, but that's the experimental colleagues are worried about. So we assume we can handle that better. We go back to here, so we don't talk about BIB here. So firstly, I want to apply EPA to the muon collider. So we got this to have a first glance to see what the general picture is. So in here, all the going down curves are for the mu plus and mu minus to this final states like W pair, TT bar pair, this Z Higgs, or this TT bar Higgs. Those things. And all the outgoing ones are the one from EPA. We notice some dashed curve going down is for the one we didn't include the ISR, didn't include the initial state radiation. The solid curves going down is the one we include the initial state radiation. We say, oh, have some gap around 10% enhancement if we include the ISR, so that ISR is important. And we also have the general picture is if we go beyond 5 TeV or even 10 TeV, for the cross sections, the vector boson fusion of the photon fusion is much larger than the annihilation. So we say, at high energy Lepton colliders, we need to pay some more attention than we expected to this VBF ones. But we also have solid and dashed curve for the going up processes, for the photon processes. That's because we take two different scales. One is for the beam energy, one is for the Hard scale for this. So we see, oh, there is a scale uncertainty. That means we want to sum those logarithms to get smaller scale uncertainty. And one more thing, is this photon to WW is maybe the largest cross section we can think about. That's the first glance. It's not accurate, but gives us some general picture. And then I want to know. I want to remind everyone. This is
sorry, just largest cross section. Shouldn't the largest cross section be muon to muon in the forward direction?
I will talk about that. So this, but you don't expect to see any physics there, right? You know that it exists. This one I want to maybe if you want to look at WW for some calculation, but I will show the one you mentioned.
Okay, and muon to neutrino. Talk
Sure.
about that. Okay,
Sure.
High energy neutrino measurement. Wouldn't that cross section be larger than this?
Neutrino I didn't include, but I include other things. But
Just
I
be careful with your statement about what is largest.
Okay, sure. So this is large. Okay, this is large. Okay, and here I want to remind everyone. So this is a study carried out by Baglow, by Manojri in the history. So that there is model-dependent, non-productive photon-induced hadronic production at the colliders. So this one is we chose the hard cross section for photon to hadrons. But we just take the formalism from two different models. One is from PCA, one is from SLAC. So this can be big. And if we fold that with the photon luminosity with the EPA PDF, we got this result. So here is mu plus mu minus to this hadronic production. This is for the E plus E minus for the hadronic production, where the red one is for PCA, green one is for the SLAC. So we say, oh, it's still model dependent, but it is big. It can reach nanobarns. That's the background. However, there's good news also from their study. So I take this from their LCD report for the click. So the events this day, here is the PT. This one is the angle, angle distribution. So events stays here. So they stay in the low PT range. So if they go above around, say 5 GeV or 10 GeV PT, we can separate ourselves from this non-productive production. But this is still the largest background, nanobarns, right? But that's not our main work. Our main work is what if we go to high PT range? What if we go to some place that we can apply the perturbative calculation? What's the thing? So this is if we take some a detector angle cut, assume we can put the detector only at 5 degree or 10 degree, and also we don't want the environment is too soft, so we put an invariant mat cut. We also put a PP cut so that we can go to high PT range. So here we count the large ones. We have E plus E minus to E plus E minus, or mu plus mu minus to mu plus mu minus. We have the lepton pair production, QQ bar production, double pair production, or compton scattering. Also, if we look at the photon scattering, we have the photon to lepton pairs, or to the QQ bar pair, or to W pair. So here, left-hand side is for the electron-positron machine, and with a 5 degree detector angle cut. Right-hand side is a mu plus minus machine with a 10 degree detector angle set. So we say, oh, the lepton pair production is smaller. Those are S-channel ones, so it goes down. The QQ bar production is larger, but it's still kind of small. This purple one is the photon to W pair. Yeah, Jen, you're right. That's not the largest, but I'm comparing that one to the signal to the background. So mu plus mu minus to mu plus mu minus. Yes, it's big. It's very large in the low energy range, but when the energy goes up, it goes down.
You know why? Because you put the hard angular cut, that's a really high PT cut on the muons.
Yes. Otherwise, you don't want to put a detector into the beam.
Well, I could put 4 detectors in my facilities.
Yeah, you're right. Okay, and so in this way, in this picture, we see this large background is actually the photon to picobar.
What's the total line there?
Total line is photon to another flavor of lepton.
Okay, so can photon go to mu plus mu minus?
It can.
And
The
where?
total specific for one flavor of lepton. So in this way, the total or muon and plus minus are all kind of the same.
There's no interference effect.
No. Why? And then, but however, you know, I mentioned we have more partons. We have quarks, gluons. We can consider in addition to this photon to picobar, we have this photon gluon to picobar, photon quark to gluon quark. We have QQ bar initial states. We have gluon quark initial state. We have gluon initial state. Apply the same card. We have this. We have this. You see, this is for again, it's for the E minus machine. This is from muon collider. We have the going down one, the black one is 100 times the lepton annihilation to picobar. That's drawing process.
Sorry, where's the WW fusion to digest?
I didn't show. Now right now we don't have we don't have WW fusion to digest, but we have gluon to digest.
They are same order.
No, WW fusion is much smaller.
For what reason?
For two reasons. One is WW fusion is you have that's the electroweak copy, right?
Electroweak PDF. Okay.
No. The threshold is very small. So here this one, if I calculate that one, I have this you integrate over tau to 1 is we see square tau is around.
Sure. Let me require the digest emergent mass to be bigger than 200 GeV. What will happen for your?
If that to be two, then those things gonna be small. I'm gonna show that later. I have one plot for that.
And do you have WW there for that?
Yeah, I have. So in this one, this one is we didn't apply those cards. We only applied this card.
Yeah,
So
it's a very soft digest.
Yeah. Very soft digest. What we want to show is previously what we thought is big. It's a big background gamma to gigabar. It's just one among those different curves, and it's a kind of smaller one. So in order to count all the background signal, you want to sum over all of them to have total digest production is here. It's one order of magnitude larger than photon to gigabar. For the muon plus mu minus machine, it's also kind of almost one order of magnitude in the previously believed largest background. So I even have a clear comparison between them. Left hand side, upper plots are for the electron-positron machine. Lower plot is for the muon collider. Left hand side is before we consider the new QCD partons. Right hand side is after we consider the new QCD partons. We just see the orange curve here is actually here. The orange curve here is actually here, and the new background is actually the real background is almost one or even two orders of magnitude larger than that one. For the muon collider is better because you involve from muon mass, not an electron mass, so it's smaller, but still kind of one order of magnitude larger than previously believed background. That's what I want to say. And as Jen asked, I answered. You have this we have this distribution. Firstly, we calculate this digest distributions. This is for the digest emergent mass. So this black one is for the annihilation. So we have Z peak here, right? Annihilation. The other ones, the colored ones, are for the contributions from these different QCD initial state. And we see that we have two mechanisms. Annihilation, it peaks around at machine energy, and also the fusion processes, they scan the whole spectrum and they peak around the threshold. And this blue one is the photon to WW. So you say, oh yeah, when this environment mass is kind of larger, yeah, you can see it's the WW product, right? And also, if we show this rapidity plot, we see the annihilation is more central, and this fusion is spread out. this is just a physics argument, and to show that how different these two mechanisms can be from each other. But this one is going to be, I think it's going to be some thing we need to keep in mind, even guidelines for future analysis. So this is for the PT distribution of this jet, one of the jet. This is for the final state energy distribution of the jet. So we see here also the colorfuls are for different jets. This black one is for this annihilation, and this blue one for benchmark is photon to WW. This blue one is for the photon to WW. So our statement is, if you go below 60 GeV in PT, the jet production dominates. Then the W pair production. If you go below 200 GeV in final state energy, the dijet production dominates. So that means the standard model electroweak sector, as well as some possible BSM physics, new physics, can only be seen in the high PT green. I think that agrees with our expectation.
Just a moment. This statement is good, but here you are comparing with final state, including at least one jet, right? So if I ask just for at low energy, what's my background rate for anything, any X, including leptons and photons, etc. Is this still the largest cross section?
Still the largest.
For what reason?
For
let's say I have a pair of photons, right? They can give me a pair of leptons very easily. Photon fusion to a pair of leptons. That's your tau curve.
That's small,
right?
That's small.
That's not that small, right? Here,
this is small. Why not?
What do you mean by small? The highest one is the one above. This is next to it. Right?
This one.
Yeah.
You're asking me why the total is smaller than kilobar?
No, I'm not asking. I'm saying this one is also a large cross section.
Yeah, that's large, but this one is here. I'm talking about the largest, not the second largest. But if you assume that one is here, right? That one is here. So in the plots, that one is going to below this kind of below this orange one. Yeah, it is there, but for the dijet, you need to sum over all of them. So I think dijet is still larger than the lepton pair. Yeah, lepton pair is there. It is there, but it's not. I mean, it's comparing to the dijet. It's smaller. Is that clear?
Okay. Okay. Let's talk about uncertainty later. Okay.
Okay, sure. We can talk about uncertainty. That's true. And then I want to show. Sorry, it's kind of over time. I want to show the full picture of multi-TeV Lepton collider. We call that not only the VBF collider, we also call that an electroweak version of RFC. So firstly, all the standard model particles can be treated as partons. Secondly, we are allowed, if we use that PDF formalism, we can even determine different polarizations. So here is luminosity for a 30 TeV muon collider. So we have gluon, quark. We even have, you see, transverse and lepton, transverse and transverse W, and the longitudinal and longitudinal W. That's the full picture. And then if you go back to apply this picture for some typical standard model processes at the muon collider, it looks like this. We have downgoing dotted ones, those are the annihilations, which at high energy they're small, at low energy they're dominant. But if you go to high energy range, the VBF, they are the dominant contribution to the semi-inclusive cross-section. And there is not only photon as a part, there's W, there's the quark and gluon, there's Z, there's photon Z mixing. But however, I can take you one thing is, in these processes, the quark and the gluon contribution is negligible because they're so small. This is like in the high energy range. You see, in the larger tau, this luminosity is less, right? And we also want to compare this electroweak FC with FC. So PP versus mu plus mu minus. So I take this from Fabio's paper. So there's a comparison on the WW luminosity. So we see those ones mu plus mu minus for the transverse, longitudinal transverse, and longitudinal, W pair. Here, those ones are from the RC. So if we consider there might be some new physics around, around here. Sorry, if we take want to produce some higher states, so we take the square root tau around 0 of 0.5, one half. Look at those things. We see that the luminosity of W pair for the muon collider is around over 4 orders of magnitude than that one for the RC. So that's why we see that muon collider of other high energy lepton colliders are electroweak versions of RC. And then I think this is just one quick example. For TTR production, we have going down annihilation, going up different fusions, and this is the total. And this is just the linear mass distribution. We see these ones are peaking at the threshold. Those are the vector boson fusions. I would say the new physics may appear here in the tails, and also the resummation effects appear here in the tails because the scale is higher. And also this one is for the annihilation, which peaks around around machine energy. Also a smaller peak here is due to the resummation. And we can also decompose different contributions to do different processes like this for the W pair, the Higgs, and TTR Higgs. So I will just quickly go through and go back to the summary. I know everyone is tired because it's so long. So firstly, physics is at very high energies, the collinear splitting dominates. So we need to use the PDF formalism to describe the thing for the future high energy colliders. Not only muon, not only collinear, but also if you think about 100 TeV hadron collider, we also need the electroweak PDF. And also the large logarithms are going to be resummed using this DGLAP equation. So the colored partons will emerge beyond Lepton. And if you go beyond this J mass of the electroweak scale, this electroweak sector is turned on. So we have more partons. We also have the corrections from electroweak sector. And the formalism will allow you to determine the polarization of the partons, which might be helpful if you think about some new physics model whose dynamics depend on the initial state of polarization. So that's the thing. And now about these high energy lepton colliders, we think those are electroweak versions of HC. So they combine the advantages of both proton collider and plus minus collider. We have two classes of processes. One is annihilation, another one is VDF, the fusion. And the main background, besides the BIB, is the jet product. So in the low PT range, that's the non-productive model-dependent photon to hadronic production. And in higher PT range, not that much heavy. Higher PT range, the quark and gluon induced jet production is kind of big. So that's my statement. Okay, thank you.
You are the host.
Yeah. So, questions?
So, returning to this WW production, you said it's much larger than the muon collider, right?
So the PDF luminosity comparison of 10 to the 4. This part is still from 5 years.
I remember some, like 15, 20 years ago, people discussed this funny process, mu plus mu minus going to WW and with the neutrino and the T channel, like the lowest diagram. And I think it's formally divergent, the cross section. There is like a singularity. Then people were puzzled by that for a while. Because you can have a like on-shell neutrinos
Oh,
Maybe
yeah.
it was in the reverse.
That's Equivalent's favorite process.
You
Maybe
can
it
have
was in the
unshelled neutrino,
reverse,
right?
W to mu, and then, but I remember neutrino in the T channel, and it gives some formally
This
kind of
neutrino
very,
can be
very
unshelled.
large cross section, and
Something like this. If
right.
you have E plus to E to E with a D, and then here you have D neutrino to sorry, D muon to a neutrino here. So this one can be unshelled because you can treat that as a D decay to two pairs of neutrinos.
That's good.
And also this is common from me to get the reason we saw the magma field is more or less more because of this unshelled.
But then how wizard deal with this? Do you know?
This part.
Yeah, why wizard give us proper result?
That part I didn't know. Because we didn't go very deep in this. We just follow this package on this.
Okay. Well, instead you should go to your PDF calculation. Go to the earlier PDF where you calculate.
Just return to the.
This one.
Is there a sensitivity to the size of the beam?
This singularity.
Yeah, where you have there are this things in sort of Weizsäcker-Williams where in certain processes you are sensitive to the sizes of the beams, like the physical sizes.
Yeah. I think that's a correction you need to add in. At the beginning order, you go to the beginning of the top of WWA.
WWA.
Yeah, this one.
You want to add some other parts, right?
Yeah, I think at this order I don't see that.
There was this corresponding discussion again 20 years ago as to what stabilizes this formally divergent cross section.
Very good.
And I don't remember the answer. I think it was the beam size or something.
It's an arbitrary scale cut choice you put in. You can argue I want to put the beam size convert to dimensional quantities.
But then there is something there is like the beam size would be like your last resort, right? For the cutoff.
Right. So later on his calculation don't have this issue because he require final state to be observable. So that's a very large PT and the angular cut.
So you're talking you need some more terms here at the WWA.
Slightly different, I think. So you recall there's a mu plus E plus minus WW divergence?
I think so. The people were discussing that, including some serious people having some discussion on that topic. It was presented at some point as like a puzzle, and in the end, of course, it's related to, like you guys said, with almost real emission on the neutrino, and I don't recall the nature of a singularity. I think it's just a logarithmic singularity. I don't remember.
Yeah.
But then, you know, if any other ways of stabilizing fail, it is the beam size, I think, that even Kirill.
Oh, that would be great. Yeah, I mean. That's I think the beam size is a more justified size, cutoff scale than this arbitrary. When you look into that, whether use like QGZ. So can we go to the PDF you calculated, including the neutrino part?
You want to show the PDF?
I want to see the PDF with the neutrino.
Yes, we didn't show this. We didn't show that. We only show this DGLAP equations because the one with neutrino, you need to test a numerical thing. We use numerical way to do this to solve the DGLAP. So it's kind of hard to give you analytic expression from.
I know, but your plot has a neutrino numerical result.
That is.
That is blowing up as well with as a muon media.
Let me see. This one. This one. It didn't show here.
I want individual one. So neutrino also blows up at x equals 1. How did you? What's happening there? What did you do with that?
That's the linear order because neutrino. The other part is.
I know.
W is solved. It's the x. That's 1 over x. X goes to 0. For neutrino, x goes to 1, so it blows up. So actually, when we were doing this, we actually gave a one cut on this x. X cannot be smaller than I think it's md squared over something like this. So by doing this, we followed the one from Christian Bauer. It's the Chris Bauer's company. They suggested to do this cut. The reason is in the literature we show that this cut gives you the double log form, the double log form, which is kind of the correct pattern. So that's why they chose this cut.
Okay, so in principle, your purple line ends earlier before 1, right?
Yeah. So that in principle, that should be for this x. That should be x should be smaller than 1 minus md squared or something like this. So we have a cut on this purple line somewhere before 1.
Okay. So there's no delta 1 minus x in there.
Yeah.
But again, in the later part, when you compare the jet cross-section contribution, I keep on asking, what's the WW contribution? You didn't show. WW to dijet.
It's much smaller.
Just go down. Go to the plot as a functional invariant dijet mass.
This one?
Yeah. So what do you mean by much smaller? On the right-hand side, shouldn't that be dominating?
Right-hand side can be. Right.
So your statement always have a scale associated with them.
Yeah.
Be careful with your statements.
So let me see. The WW to dijet, we can start around 2 W's around here, like this.
Why is much smaller than the photon to WW plus W minus cross section? Why is much lower? I'm asking. Why is not larger than the light blue curve?
That part I don't know. I just want to show you the shape. I mean that's.
I'm asking about the size, right?
Size I cannot answer before doing the calculation, so I'm not sure whether it's larger, but.
And why you didn't do the calculation? Here it seems like you only do QED plus QCD. You didn't do you only do EM plus QCD, right?
Yes.
You didn't do electroweak plus QCD.
Yes, because we focus on this part.
Right. Then you shouldn't plot the region about 200 GeV. That's your formalism fails.
Well, that's a good suggestion.
And it's about physics correctness. You shouldn't plot. There's no statement you can make on the right hand side.
I mean, even if this WW to dijet is just around here, it still gives you the statement that you don't want to look for the electric spectre for WW production in this range. We just want to know. We just want to say that in this range you don't see the WW production.
I mean, about 200, you are not going to have fair statement on many processes.
That's sure. But that thing you're gonna the thing is you're gonna if we include WW to dijet, I'm gonna push this from 60 GeV to maybe 70 or something because you have more background from dijet. So that's more or less that.
Yeah, that's from that on. Your statement is your cross section drawing is incorrect. Right?
Not incorrect. It's not. It's incomplete.
Yeah, sure, incomplete. Incomplete, and your claim about who's dominating is incorrect.
No, because we didn't focus on this. Because otherwise, you can ask me one more question.
Yeah.
Why don't I have WW2WW?
I asked you earlier already. You didn't answer me.
Why don't I have WW2WW? We have WW2WW here, but we didn't have WW2WW in here.
Oh, because you didn't include the QED PDF.
Because this is only roughly give us some feeling. We won't go beyond the 60 or 70 something. So this is in this work we focused only on this low energy range. But this one is on the full range.
So far you give 0 physics examples, right? To say it changes our expectation for certain physical process, precision or measurement by a huge amount, right? So I think it'll be interesting to work out the real physical impact of all those PDFs.
Yeah.
Either positively by saying I increase the cross section for certain BSM by a lot, or negatively saying certain precision program is going to be heavily worsened because of those additional background. Yeah.
That's very good suggestion.
Yeah. And the leading order example you should work on is the Higgs precision program. The Patrick Mead et al. Claim the 10T muon collider can be a decent Higgs factory. They of course don't have those multi-jet background at low energy, but the Higgs factory is Higgs is at 125 GeV. So that's exactly the scale where this new background or more corrected calculation background is much more larger. So their Higgs factory statement will be wrong or heavily corrected by your work.
You're right. Yeah, but by doing this, we think we want. I mean, this one by drawing this plot, we think we want to just say out the one voice that there is colored partons behind these leptons, which is sometimes people don't think about, and we just focus on that part. We didn't do this as you should suggest.
So one conceptual question. Okay, so I start with the unpolarized muon beam. Okay.
Yeah.
During the electric PDF evolution process, will my beam become spontaneously polarized?
It is polarized.
Okay, so why don't you show us the polarized muon PDF? So I start with the unpolarized muon, right? You show the PDF of plus and minus helicity, they will differ, right? So it's actually an interesting case. You will say the spontaneous polarization for any lepton collisions through the electroweak interaction.
Yes. So I actually twofold. One is for this thing, as you commented, in low energy range, it's mainly QED and QCD dominant. So this polarization thing doesn't show up, and it shows up here, but I didn't show. But in calculating those things, that we separated the polarization. And you're right, as the statement was made by also us in private communication, also by some papers by Chris Bauer's company in their paper. They say as long as you turn on this electroweak sector, you have the W and Z radiations, and the couplings are different for left hand and right hand fermions. And also splitting kernels are different. One is 1 over x, one is 1 minus x squared over x. And then finally, even gluons will be polarized. So if you think about the reason why we think about unpolarized thing for the PDF for today is because we don't have a polarized hadron collider. We don't want to make things so messy. So and also in QCD, there's a left hand, right hand, the coupling that's same. So you just average sum over that's okay. Otherwise, if you think about if you think about the photon collision at IOC, you need to think about you need to take the polarized PDF even for the EPA. And even for unpolarized muon collider, since if you think it's really electric dominant some processes, you need to take into considerations of this polarization effect. Thus, we included that here in the calculations, but I just didn't.
But there is no cute case that you can make out of it beyond its more proper calculator of the cross section.
Yeah. And also there's something we didn't include in the first papers because they treated all the quarks as massless. We treated all the leptons as massless, but actually, the tau is much heavier than muon. Muon is much heavier than electron. The quarks are different. There are some many thresholds in the evolution. That part we didn't include yet here. So this line we just want to roughly show what the picture is. But if you ask for more precision, more resolutions of the picture, we are working on that. Still working on that.
So any new? Okay. If not, let's send our speakers. Okay.